Okay. Hello, everyone. I hope that everyone is back. And so we will now start again with the next two demos. And so actually, I was now trying. So now, just in the during the break, actually, I was trying to run the demo that I had created for creating a shell. So that time, the demo that I had created, actually, it's not working now, right now. And I think I thought that if I run it with GDP, that the ASLR is disabled by default and every time it's going to run same. But I was wrong. So even when they're running with GDB, it also runs a program with ASLR enabled. And so that's why even with GDB, the layout of the program, like the stack or something, will be changed, stack, heap, etc., will be changed. And that's why even with the GDB enabled, you can get like different locations in the memory. And so the best way, I think, to do this kind of like to do these kind of a demo or learn these exploits would have been to create a VM and then disable ASLR. Although we can do enable it, disable it on our machine as well, but I think uh, I would not advise to do so. But so to do it, like to then like if you want to try it, then you can do it you can create a virtual machine, you can disable there. I mean, for the next time, because I'm going to do that from next time only. But for now, although this demo that I've not created, that I had created is not currently working, but let's say if we, so we will try to fix it. Okay. So let me first explain what the demo is about, and then we will try to fix that. So first of all, here we have this. So this is the file that we have. So this is the same code that we had earlier, but earlier we were taking this input from the command line. And now instead of taking it from the command line, I have actually created a buffer in the main. And then I'm passing this buffer to copy it to the buffer in copy buff function. Of course, you can think of it still like such a buffer, like such a crafted payload or a crafted input can be sent to your program via command line or network or anything. But I just found it easier to write it in this way here, because then I won't have to write all of this in the command line. Okay, but you can, of course, generate a byte sequence like this, and you can then pass it to your function as an argument. But what you have to take care of is actually the layout. So not the layout, basically, how your values are going to store into your program, uh, like in your stack. So there are these two different so there are, I think, the different formats in which the values are stored. So the like currently the values in this system here, it is configured that the values are stored in the little Indian format. And in the little Indian format, the values are actually stored in this manner. Like you have, like, if this is your original value that you want to store, so you're not going to write it like this address, you are not going to write as it is. You have to write it in the reverse order. Not exactly in the reverse order, actually. You're going to write first two bytes FF, then the next two bytes FF, then D2 here, and then 90s. So this is in the little Indian format that we have to specify. Now, a bit about, of course, you understand the rest of the program, because what this we were. Okay, I am so sorry. I forgot to share the screen. Okay. Yeah, I'm very sorry about that. Okay. Okay, so I will restart. What I was saying that this function is this program is same as before. So we have the main function and the copy buffer function, which we were seeing in the last buffer overflow program also. There we were taking the argument from the command line, and we were passing that argument to the copy buff function, right? argv1 we were passing. But here, instead of that, what I have done is that I have created a buffer here, and in the main itself, and then I have added this like I've added the I've created this buffer, and this is the content that I filled in this buffer, which and then I'm going to pass the address of this buffer to copy buff function, and then it is going to take this. And here in the copy buff function, I have allocated like I have created a buffer of size 64 bytes, and this is more than 64 bytes, of course, and so this is going to rewrite the this will cause a buffer overflow, and this is going to rewrite the adjacent memory locations on the stack. So I hope that this is visible now. The screen is visible now. Next, what I was saying is about the Little Indian format. So the values on your stack will be stored in the Little Indian format, means that this address FFFFD290 is actually not, if you want to store this value on the stack, uh, you will have to create a byte sequence like this. Okay, so you will have to write it in the reverse order, reverse like these two bytes. So first you will write here 0x90, then 0xD2, then 0xFF, and then 0xFF. Because you will write it like this, and then it will be stored like this. Okay, and so what are the other parts? So the first, initially we have added just some 0x90. What does 0x90 mean? 0x90 is the opcode for NOP instruction, the no operation instruction, which does nothing. So we have added a lot of these bytes, uh, like byte sequences here, which is just going to be treated as NOP instructions. After that, in the middle, we have this approximately, I think, 13, no, I think this is 13 plus 13 plus some 26, 27, 28, 29, 30, 30. So this is like 32 uh, bytes here. Okay. Yeah, so this is what we have, like 32 bytes here. And these 32 bytes are actually your shell code. So when we were looking at the slides earlier, we had looked at the sequence of instructions, right? Let me just go back and bring back the slides. Yeah. Yeah, so we were talking about creating a exploit program, which is going to invoke a shell, right? So to invoke this shell, what we were saying uh, was this is what we had discussed before, right? That we are going to write a if this is the program may that we have written in the, like, basically this is the program. In the function main, we have calling execve library call, and this library call is taking these two arguments, name 0, name and null, sorry, three arguments, and then it is going to start the shell /bin/sh. And then we looked at the disassembly of the main function, and then we saw that this disassembly is actually calling here what execve. So the call to the execve is there, and then we had looked at the execve disassembly here, that it is making a system call, and these are the arguments which are being passed to the system call, like 0xp. This, I think, this is going to indicate that which system call to execute the system call number, and this is going to these are the arguments to the system call. Where EBX, ECX, I think these would like they would contain the address of the /bin/sh string, and then int 80 is the trap instruction, which is going to which is going to get trapped, and thereby your control will go to the system call handlers, and the system call handler will execute. Now what we have done is we have created a payload. We basically created a sequence of such instructions, and these instructions like this we so for to do so, like to create invoke a shell, like what we have is we have the basic requirements, like we need a null terminated /bin/sh string, and then we need to know the address of this string. So then we will copy 0xb into AX, then copy the address of the string, copy the address of the string in ECX, and then the address of the null long word, which is the third argument. And then we execute int 80, the system call. So this will, so then we can create something like a attack payload like this. Okay, like there will be like move L string address comma string address address. So it's moving the string address into here. So this is then, or otherwise, which I think whatever. So then we are going to get this. Then after this, there are these sequence of instructions where we have already looked that we are moving the value P in EAX, which is going to represent the system call number, then moving the address of the string in EBX, then computing here the address of the address. So this is moving the address of the string. This is computing the address of the address where the string is located into ECX, and the address of the null string into EDX, and then we are calling int 80. And so this is where your string is actually located. So this is how basically you can then create a sequence of instructions. Okay. And so I have not done it myself, like I did not create it myself. I looked at some other sources, and I got this, say, sequence of instructions which will be invoking the shell. Okay. And of course, we were discussing earlier that there can be many such attack sequences, or because x86 gives us the flexibility, like there are so many instructions to do the same thing. So then when we have this sequence of assembly instructions, we will then convert it into this byte sequences, hexadecimal byte sequence, which we then are going to copy here into the buffer. So this is corresponding to the shell invocation code. Okay, it will invoke the shell. So this like 0xcd is 80 is, it's like a int 80. Okay, and it's like here 0xcd 80. So this is like int 80. And after that, so first we have here put some padding, then we have added our shell code, and then again we have say we there is still some, say, like now we have to overwrite the return address to point to the shell code, right? So before the end of the shell code byte sequence, and before the start, and in between the, like in between the end of this byte sequence and the start of the return address, there can be some other bytes. So we have just put wrote there the garbage A value. Okay, so this is like how we have created a byte sequence. And if we will fill this return address correctly to point to the correct address, like to point to our address inside, somewhere inside this, basically, if we place it anywhere from this sequence till here, then it should call the it should it should start the shell. So that is what we are trying to do here. So now, hmm, let's see if anyone has any questions. Okay, so if there is no question, then let me try to run it with the GDP. Okay, just give me a moment. Okay, yeah, I am sorry for that. And so how you located the address of the shell code? We are going to locate the address of the shell code. Now, at the time, actually, when I had created the demo, like at that time, I had looked at the stack. So, so looked at the stack and then I filled the address. So there, if we look at the code again, so these are all the NOP instructions. Okay. So adding these padding, like adding these NOP instructions in the like byte sequences in the beginning gives you the flexibility to add to like point this address some anywhere here. So if you point it here or here or here, anywhere, if you will point the address, then it is fine. Because initially the NOP instructions will be executed and then finally your stack, sequence, so shell code. So that's why it will give you the flexibility. And so how do you determine this? So I had to look it up in the GDB, have to check in the GDB that where is my buffer located, how is it getting filled, what address should I give so that it just jumps there. And where, of course, like earlier, what we were trying to see, right? How many bytes we will have to write so as to rewrite the return address. So this number of bytes also we will have to find out. Here currently, I think I have written 20. These are 20. These are 32 bytes, and this is I think 20. 6, 27, 28. I think this is 28. This is 32 bytes, and this is 16 bytes. So currently, which is how much? 76, right? So currently these are 76 bytes, which I've written here, and which means that from the starting of the buffer till the return address, where the return address is located, there are 76 bytes of gap. I hope that answered. If not, like we will actually be looking at it, and I hope that will answer the question in a while. So we are going to start it with a GTB. As I was saying that actually it's not working, but let me still like try. So it's giving a segmentation fault right now. And let's now try to debug this program. So let's first list the program and let's try to break it at line number 6. Okay. And then we are going to say run it again. And then in the, so we are passing the string located at this address. And this is the, uh, it's saying that it is repeated 28 times. And then this is the sequence. And so now let's look at the disassemble. Let's disassemble it and see. Where are we? So we are currently here in copy buff. So we can see this instruction is of interest to us, and this instruction is like ESP 44. So it's allocating here 68 bytes for the buffer. Okay, like it has subtracted basically ESP by 68, and here our buffer is actually 64 bytes. And now let's look at the content of the stack. We'll look at the content of the stack. So first, let's try to find out where the address is, return address from the copy buff. So the return address from copy buff, I think it would be like this only, but we can also check. So we have disassembled main, and in the main, the address of the instruction after the call is this, right? So did I? So that is okay. So this is all, yeah. So this is your return address, and this is where your return address is placed, right? So now let us look at the info registers. EIP, ESP, EVP. So EIP is going to point, is the like instruction pointer, which is inside the copy buff function. ESP is your stack for top, which is here, and then EBP is D2E8. D2E8. So starting from here. E0, E4, E8. So this is starting from here. So that's D2E8 is your EVP, and this is your ESP. And now let's look at this symbol, it. And so far we have executed these instructions. Yeah. So now let's try to like execute the string copy, and then we will see where it is getting copied. Okay. So then let's add the breakpoint after the call is executed and continue. So the call is finished. And now we are here. It's our stack. So if we can see, it started writing from here. Okay. And then this is what it has written. And then it's what's writing. And hmm. Okay, so what was our return address? How did the stack look before? This is how the stack was looking. It was here D2, E0, E4, E8, and here EC, I think. This was your return address to the main function. So which we are trying to change. D2, E0, right? Yeah, this line. And this the last column here in this line, D2, E0, it is your return address. This we are trying to change. So this we are changing here and we're setting it to FFFFD290. So now, but the actually this is wrong. It's being set a bit wrong. It's being set here D290. We have to set it to D2A0 or A4 so that the program will run and execute. So let's try doing that. Uh, yeah, although the problem is that for that I'll have to compile it again. But let's see if that works. So I'm going to continue it run and yeah. Okay, so maybe before I do that, did you understand how I am here finding the location where the return address is stored, which we need to modify, and then what value we are going to modify it with? I hope those two things are clear. If not, just let me know. And let me just try to change it to D2A4 or A0. Or in fact, like B0. Let's see. Hmm. Now here, let's run it again. And let's see. Yeah, so now it's working fine. So if you will see now that we changed the address, so which now I think is correctly pointing to that. And we have here spawned a shell. So it is starting when we run this ADDR program, we are actually starting a new program. And this we were saying, now we have created a shell. And since we have created a shell, we can actually do anything now. So I can list the files. I can pretty much, let's say, check what processes are running. Like I'm running this bash process, like this sh is actually corresponding to this new process which is creating. Okay. And or GDB is running because GDB is running my original program here. And so this is how we can create the shell. And of course, we can read any files now, which is going like the vulnerability. So I hope, yeah, I will explain it again. Now once more, now that it's working. So let's now just run, like quit from the, now we have quit from the shell. Okay, so we are going to, let me just look at the go from, let me just look at, open the code again. And I will try to explain it here from the code first, and then we will look at the stack. Okay. So what we are trying to do, the goal is to create a shell. So see, this is your program, right? This is your original program. In this program, consider that, see, currently here I have added this buffer, created this buffer right here into the main program. But that's not necessary because this buffer input can come from the network, or it can come from the command line as we were doing earlier. So the buffer, so what we are passing it here, I have set it to a specific value here, like engineered payload. It's a payload, attack payload. What does this attack payload contain? This attack payload fills, like first it contains a sequence of in these byte sequences, which like basically will be translated as NOP instructions, no operation instructions. Then there is this byte sequence, which will be then which will basically invoke the shell. So it is corresponding to starting a shell, like calling this, making the system call and giving it to the address of the string slash bin slash sh that we were seeing. And after that, I have added some padding here, not say padding, but some arbitrary values here until the return address, because we are interested in changing the return address. Now here finally, um, like so here finally I have changed the return address such that, like I have basically created this byte sequences here such that it is the address of some it is the address of some bytes which are located here initially here, okay, in this section corresponding to just NOP instruction. Now there are two important things here. The first thing is, of course, like I think the three important things. First, of course, if you want to do something like this, first of all, you will have to create this shell code, okay, and convert it into this byte sequences. Okay, that's the first step. Then the second step would be to find this distance between the buffer start, like from where the buffer is going to be written, till the return address, because you have to write that many bytes. So here, actually from the start of the buffer to the return address, there are 76 bytes. Although the buffer is only 64 bytes here, but there are some additional bytes in between, because 68 bytes were allocated for the buffer, and then there will be EBX or EBP or EB or ECX or something. Something will be pushed onto the stack. So that's there. After that, we have to change the, after that there is return address. So then we are modifying this uh, return address which is stored on the stack with this value, with this byte sequences. So here we have to write the byte sequences in the reverse order, because the stack on the data, the stack, because on the stack the data will be stored in little Indian format. Okay, so if we give it in the reverse order, then it will store it in this way correctly. So here, so here initially, like earlier, basically this program was not working. Why? Because the return address was not correctly the return address was not correct. Because when I was preparing the demo at that time, I had done it with GDP and I had found the address. But now then today I was running it with GDP, the address was changed. So that itself shows that the ASLR is in place and it is changing the addresses of the stack. So which will, as you can see here, will even stopped me like from creating this. So similarly, every time the program is going to be run, it changed. So that's like you were, I think, also able to see ASLR in action. So now, how do we find out where the address is? So that here what we did was that we first ran this program with our like there is no input actually. We first ran this program, and currently it's actually going to start again the shell. So we will have to first add these breakpoints actually. I don't I think because the shell is there, it's not, the list command is not working anymore here. Okay, then let me start GDB again. I hope that it will still work. And let's first list the content of the file. Then we will put the breakpoints here. Uh, so now I am going to explain how that buffer that we have created is going to be stored and how how that address was computed. So I'm just explaining everything again. Okay. So we are going to add a breakpoint at line number 7, say. Then we are going to run the program. Then the program will run. Then let's see where we are in the program currently. So we are here. So and the call instruction is here. So let's just run the program with like 1, 2, 3, 4, 5, 6. So let's run the program up to 6 instructions. Now we are actually already into the string copy function. But let me add a breakpoint because we want to inspect the content of the buffer, right? So let's add a breakpoint here and then continue. So the copy buff function would execute, not the copy buff, I mean the string copy function would execute, and then we will return back here. Now let's look at the content of the stack. So this is your stack now, okay? And here in your program, you have given this byte sequence as buffer. So this byte sequence will be written on the copied on the buffer, right? So 0x90, and so first these 16 plus 8, no, 16 plus 12, 28 bytes are copied. After that, your shell code is copied, and after that, your AAA byte sequence is copied, which is 16 bytes. And lastly, the return address, which was earlier placed here, has been now modified with FFFFD2B0, this address. And so when you will now execute this program, continue to execute this program. So let's look at that also in action. So we will execute first this add instruction, then the NOP instruction will happen, then one more. And then let's look at the value of the stack, values on the stack. So now the values on, this is the top of the stack, which is the start of the buffer, and this. And next, let us execute the leave instruction. So when the leave instruction will execute, then the buffer, basically the uh, area for buffer which was allocated. So your ESP pointer will be moved up. So that's why all of these values will be removed. And now what is there on the top of your stack is the return address. Okay, and now what is there? Can you tell me what will be there in the EBP register now? If you are able to follow this so far, can you tell me what is stored in your EBP register and what will be stored in your uh, not ESP. ESP you can see here. So what is the return address and what will be stored in your EBP register? What is stored in EBP? So the leave instruction executed. It has changed the value of ESP. Now this is the top of your ESP. I mean top of, not the ESP. This is the top of your stack. The question is, what is the return address and what is the EBP? So the EBP is F2F68. F2F68. F. Where is this value? F2F68. Can you F2F68? How did you find out that this is the value in the EBP? I mean, why are you saying this is the value in the EBP? So, uh, this was your stack. Okay, this was your stack earlier, but this is after the string copy, actually. Before that, I did not print the stack this time. So, so this is your return address that we have put on the stack. Okay. And as we have seen before, when in the layout of the process in the slides also, so what we are doing is that first the return address is pushed right on the stack. After that, the EBP, the current EBP value is put, right? And then when you are going to return back from a function, you are going to restore the value of the EBP by changing the value of the EBP equal to what was stored earlier into the on the stack. So this is actually a previous EBP value which has been modified. Okay, we have just modified it. So now actually if you will look, try to uh, print it, you will see that the EBP value is 41414141. Because why? Because we have rewritten when we are adding this buffer, right? When we are writing into the buffer beyond its size, then we are changing the EBP also, which is beyond. And but here in this particular payload, we have only like carefully modified the return address. We have modified the return address to point here on the stack. So this is D2B0. This is D2B0. So what will happen is then when the function copy buff will return, it will use this as the return address and it will start executing instructions from here. Then it will execute these in byte sequences. And 090, sorry, 90, it will treat as a NOP instruction. And then it will execute these sequences, which is the shell code. And that is how the shell is getting invoked or it started. Does that make sense? Is it clear now? Uh, is it clear now? So you can try the shell invocation address, how to get that. So you will have to, as I was saying, right? Particularly for this demo, what you can do is that uh, you can start the program in GDB. Then uh, you can inspect where your buffer is located. Okay. And so here the buffer is located at starting from address FFFD2A0. And this is your byte sequence that you are going to write, like from here 90 till here. So this is the byte sequence that you are going to write. So the address, the return address, you can point the return address to anywhere in this range. You can set it to D2A0, A4, A8, or actually like A2, A1, etc. You can point it to any value within this sequence. For this, you of course need to know where your buffer is located, from where you're starting to write these. Does that answer your question? Does that answer your question? So is that clear to everybody? Can you try this demo like after no op? Middle part of the address, which is after no. How did you get? Which address? Can you tell me here which address you're talking about? Like, I'm not able to. So this is the return address which I've changed to. I've set it to FFFD2B0. Your stack, like on the stack, your buffer is starting from D2A0. So can you tell me which address you mean? Not in this, not in the code. Which one? What did you special invocation address? Which address are you referring to here? So this is not the address. This is the shell code. So this is the byte sequence corresponding to the invoking the shell. What we had looked at, right? This is not the address. This is, okay. Memory. Yeah, so that is not the address. That's actually, if you will, if you want to invoke the shell, then you will have to like do such. So this is required that you have to execute a system call and you have to pass these arguments to the system call, and then you can create a attack payload. Like you can write a assembly code and then you can try it out. You can write your C code. Inside the C code, you can create a ASM. You can write assembly code inside the ASM pragma, and you can write this code, right? And you can try to see whether so like basically first you can write this. Okay, you can disassemble this. This will give you some instructions sequence which is required to call the shell. But as we saw that this is actually going to call the library function. Now then we look at inside the library function, like how the library function is calling this shell. So it is actually making a system call, and this is these are the argument to the system call. So then we understand that what is the requirement for this. Then you will create a attack like you will create this sequence of instructions, and then after that, the instruction sequence you're going to create, and then you are going to convert that instruction sequence that you have got into the bytecode. Like basically, you're going to create a uh, machine code of it, and then you're going to put the machine code there in your buffer. Does that answer the question? Right, so it can be different also. Like here, the code is something different. The code that I have there is different. So it can be different. Uh, so currently I don't think I can show how that, because I did not create that sequence on my own. I got that from another demo. So that's why I cannot show you that sequence right now. Okay. So if there is any other question, or if everything is clear, then we can move on to the last part for today's session. Uh, in Okay. Yeah. So I will encourage you to try to create that sequence, the shell code. So for that, you can try to uh, like these slides, or you can like the code that I have, the shell code basically, you can convert it back to the assembly code, and then you can understand that code, and then you can try to convert it back to the machine code. So now let's move on to the defenses. Okay. Mm. Yeah, so we today like have talked about these three defenses for buffer overflow exploits. The first one is W XOR X, or uh, non-execute bit, or the data execution prevention. It is also called, like there are different names for it. It's called data execution prevention, or DEP, or non-execute bit NX, or the W XOR X. So it prevents the executable stack and the writable code pages. So that means the stack is not executable, the code pages are not writable. And by default, it is enabled, but we can disable it using this flag -z exec stack, which we have done actually in our demos. So we have disabled it. So that's why you are able to run the shell. Okay, but if you will enable it, like if you remove this flag and if you try to run compile it again, and if you try to run that, then you will not be able to execute the shell code which is written on their stack, which we have put on the stack. Then the next one is stack canaries, which detect the buffer overflowing. And then we have seen that it is done by adding this random data onto the stack soon after the buffer size. Okay. And it is added by default by the compiler. And we have here in this demo, for the purpose of the demo, we had disabled it by using the flag -f no stack protector. And if we going to, let's say, enable this flag, then we will see that if we enable the stack canaries, then we will see that we are no longer able to do a buffer overflow attack. So we can actually see that. And so inside the make file, let's instead of minus f no stack protector, if we changes to minus f stack protector and make it and if we make it and then try to run this, then it will give a stack smashing detected error. So it has been terminated and you get this warning here. Okay, and similarly, if you will remove the flag and now the stack is no longer executable, and then if let's say we will compile it again and so the canary are not there, okay, currently, but we have disabled thus like we have enabled W XOR X. So the stack is now non-executable. Now, if we will run this program now with GDP, I will run it here only. Now, so first of all, I think it's just giving this segmentation fault here. Yeah. So it's not running, it's giving a segmentation fault here because now it's no longer a valid address because this is the address of on the stack and the stack cannot be executed. Next is ASLR, which is address space layout randomization. And it randomizes the location of various modules at each run. And like if the stack, heap, libraries, your text, etc., everything, so that the attacker finds it difficult to find the location of the payload. So which was also happening earlier. So and the status of the ASLR, whether the ASLR is enabled in your system or not, that you can find in this directory /proc /sys /kernel /randomize underscore v underscore space. And the value 0 here will indicate that the ASLR is disabled. And to enable an ASLR, we can change the value to either 1, 2, 3. And to change that, you would need the sudo permissions. So let's look at this. So currently the value here is 2. And so it's enabled and this will prevent the attack because the location of all the modules will be randomized on every run of the process. So that's the 3 defenses that we saw and how we can disable or enable them. And this that's why they work. Now for the stack canaries in particular, we can actually see that uh, like let me enable the stack canaries and then we will look at the okay, sorry. So we have enabled here the stack canary. So now let's look at this file again. Okay. So this is going to, let's say we will add a breakpoint anywhere, and then we are going to run, and we hit the breakpoint, and then let's say December 8. So you will notice that there is some additional code which has been added now, okay, in the program, which was not earlier there. So if you will see here, these are the additional code lines which are actually checking, like here EBP minus C. So EBP minus 12 bytes, that value is moved to AAX register. Then the value of the EX register is compared with some value which is stored in the global, I think the global offset table here. And then after this, you're you are going to subtract these two values. And if these two values are same, then you will jump equal. Like if they're equal, then you're going to jump here to the next instruction. And if they're not equal, then you are going to jump to a stack check fail local function, which is detecting the stacks buffer overflow. Okay. And then, yeah, I mean, I have just some more information exactly about the code here, which I've actually already explained, but you can also find this information here, right? So it is performing a stack canary check to detect buffer overflow attack. So this is uh, checking the value. Yeah, so actually that is related to here. So because first we have to store the value of the stack canary on the stack, and then we are checking it. So the store is also happening somewhere here. Yeah, here. Here the stack canary is being stored. Okay, so the value here is moved to ECX, and then the value in the ECX register is moved to EBP minus C. And that's what you are actually checking here. So then this is a mechanism, or this is a defense which is implemented by the compiler. So we did not have to do anything. The compiler generated this additional code, and then it is putting the canary. So with that, I have finished the like the demos related to buffer overflow attacks, and also looked at the defense, how to enable, disable, how can you check whether a defense is enabled or not, and what these defenses are, and just inspected that stack canary enabled program binary. So if you have any questions from today's content, then you can ask me now, uh, because from 6 to 7 now I'll be available to take any question from today's session. And if you do not have any question, then we will end the today's session at 6, and then we will meet tomorrow at 10 a.m. And I will encourage you, if you get time, then you can try these demos. And if you uh, like try them, or if possible, in a virtual machine, you can create. And uh, so can you, so regarding the recording, can you go in your chat and see if the recording, if you can see the recording of the last session or not in your chat? I'm not sure if all the participants are able to see the recording or not, because it's available for me, but I'm not sure if it's available to you or not. Can you let me know if the recording is available in your chat or not? If it is not there, then I will put it on YouTube, and then I can send the link to that. Yeah, I can explain that. So yeah, sure, I will explain that again. So let me enable the, so disable the canaries. Okay. So let me see. Yeah, so it's working, able to invoke, but then we are not able to do anything else into the program. Okay, so we are, let me just see if there is any other question. Okay, no, sorry. Mm, yeah. So I'm restarting the last demo, which is creating a shell. Okay. And now I'm going, like, we are going to see again how the stack is going to be filled with our payload that we have put in the buffer array in the main function, which is being passed to the copy buff function. And the copy buff function has the str copy to copy the incoming buffer into the buffer it has as a local variable. Okay, so for this first, let's try to, we will add some breakpoints here. So let's add a breakpoint here on line number 7. Mm, 6, let's add a breakpoint, and then we were going to run it. Okay, and then after that, we are going to, let's say, disassemble this program, and we're going to disassemble this program, and currently our EIP, the instruction pointer, is pointing here. Okay, so the next instruction, if you do a SI, single instruction execute, then this will get executed. But what we are interested in is knowing that how will the stack going to change after the call. So first, let us just do execute 1, 2, 3, 4, 4 instruction. Let's say execute and see how many, where are we. So currently we are on the move. And let's see, let us inspect the content of the stack. Okay. Uh, so then, but before I do that, let me just do one more thing, is to disassemble main. So we are going to here like disassemble, we have disassembled main, and this is actually the return address in the main from the copy buff function. Okay. So this is the call to copy buff. And in the main, we are going to return here. And this address will be placed on the stack, right? This address is already present on the stack. Why am I noting this address? So that I know, like, so that I can recognize the location of the return address. I will try to find it here. Okay, so then I'm going to so this is the return address in the main after the call to copy buff. Okay, and so currently we are here. This is the copy buff function. Currently we are here in this instruction, and we were looking at, let's look at the stack content. So this is how the stack is looking. The stack, top of the stack, which is the ESP register, it contains the value FFFD290 info registers, ESP, EBP, EIP. Okay, so your ESP, which is the top of the stack, has this value FFFD290. And your EBP has this value FFFD2E8. Okay, D2E8. So this is D2E0. This is D2E4. This is D2E8. Okay, this is here. And this is your EIP, that is the instruction pointer. Now, and this is your return address in the main, which we had noted here, 80484FC. This is the return address. Now, and what is this? If you recall earlier, what we had when we had actually looked at the slides. So if the stack frame contains the return address followed by the value of the EIP, the value of the previous EIP actually. Like exactly, I think. Like initially you're going to push all the arguments, then the return address is pushed on the stack. After that, the value of EIP is pushed. Sorry, not EIP, EBP is pushed. And then the value of EBP is made equal to ESP. Okay, so the value of EBP is stored here. So this is the value of the EBP. This is the return address. And now when you are going to write the buffer, so the buffer is, say, starting from here, D290. Now, when you are going to write the buffer is 62, 68. So when you're going to start writing the buffer from here, and since your buffer, the buffer that you have created, the content in the buffer is more than what the buffer can, sorry, what you are trying to copy into the buffer is more than what the buffer can hold. Like the buffer can hold only 64 bytes, but you are writing more than 64 bytes here. So that's why buffer will overrun, right? So when the buffer will overrun, it will change these values, including the value here. So this value will be changed. So remember the address of this value. The address of this value is actually this only. This is the address of previous frame pointer, which is like the address of current frame pointer is this, and the current frame pointer contains the value, previous frame pointer value. Okay, so let's now try to run the program and try to execute this call to str copy, and then we will see that how the value is going to change here. So then we are going to say break, set a breakpoint after the call. Okay, let's set up a breakpoint after the call. Why are we setting a breakpoint after the call? Because we want to stop the program here so that we can inspect the content of the stack after the call has happened, right? And then we are going to continue, and then we are going to say inspect the value of these registers. Okay, so the address values of these registers are currently what? They are same as before. Uh, yeah, D290, D2E8, and the EIP has been changed. EIP is now here. Now, what is there on your stack? Now let's look at that. Now your stack here contains this. So your buffer was starting from here, D2A0, and your buffer has been filled, and this is the content of your stack right now. So this is the content of the buffer which you have copied. Now the address of your previous frame pointer, like the value of your previous frame pointer was actually stored here previously, and that was this value ff f ffffd378. This was the previous frame pointer, which has now been changed to 0x41414141. So that is why, because it has been changed now, when the leave instruction is going to be executed, which is going to read the value from here and store it in EBP register, this value gets stored into the register. And then the return instruction is going to read this value and use it as a return address. So we can do that and see actually where are we exactly right now. So let's say we are going to run 3 instructions. So we have executed the leave instruction. And after that, if we look at the registers, ESP and EBP. So now your EBP register contains value 41414141. Okay. But earlier was like, it was pointing to the current stack frame. Now it is because we are leaving this current function and we're returning to the previous function, it is trying to restore the stack frame of the previous function, which is main, and it is reading the previous stack pointer from the stack, uh, but that is corrupted with value 414141. So that's what it is going to read. So I hope that made it clear. If you have any other question, or if it's not understanding anywhere, actually, if you're not if you're not able to follow at some step here, then you can tell me which step you were not able to follow. Okay, that's great. So if you have any other question apart, like any other question, then please feel free to ask. And if you do not have any questions, then we can end the session here and then start tomorrow at 10. Then tomorrow, I think we can start with some uh, exploits like format string vulnerabilities, and then return to libc, return oriented programming. After that, we will have demos for these, and then we will look at some defenses for these, like control flow integrity and memory bound checking. And if we will have time, then we will cover SFI or attestation later. And I have actually not been able to create feedback form. So if you can just give me a few minutes, let me just create a feedback form which I can share with you now, and so that you can give me the feedback. Just wait for a few minutes. I think me, or I think nobody replied to me here that whether you can check, see the recording into the chat window or not. Can you just let me know? Do you see the recording in chat? Okay, so you can't see it. So then, okay, I will download it and then I will try to share it. But let me first create this form that you can fill, and then I will send this to you. Uh, I will send the recordings link to the recording as well. I am. Let's see. Yeah, I am. Let me copy the form. This is the link to the form, and I have not added many questions here. But if there is an open question where you in the last we can add anything, you can add your name and email ID. It's optional. It's not necessary. And but for all of you who are actually present in the mail in the meeting right now, can you leave your email IDs in the chat so that I can send you the link to the YouTube videos. Thank you. So you can leave your uh, mail IDs in the chat box. You can uh, fill the feedback form if you want to give any feedbacks. It will be good if you can fill it, uh, but otherwise it's also fine. Is it asking for permissions to fill the form? Okay, I think I have to change. Probably it's because my organization. Yeah, I think I have, sorry, I have changed it. No, it should be fine. Yeah, it's fine now. Okay, thank you, everyone. Thank you so much. I will put the videos. I'll try to upload all of these videos on the on YouTube, and then I will send the links. And I have already shared the link to the GitHub repo. I hope you were able to clone it, and then you can try these example demos if you have time, or you can try them later as well. Okay. Thanks, everyone. Uh, yeah. 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 So we can leave the class. It's over. Let's meet tomorrow. I am just here if you have any question. And I've actually shared the form. This is the form. Copy. This is the feedback form that you can fill. And and you can leave your email IDs here so that I can send the recording. Okay. And thank you everyone for joining. I hope to see you tomorrow. Okay, I will stop the recording and then we will end the meeting.